Hi, everybody, and welcome to yet another recorded Zoom interview. Our guest today is in Rapid City, South Dakota, Trevor Waldien. Trevor, what's the weather like in Rapid City this morning?
It's good today. It was hot yesterday, but the here in the mid-continent, it's up and down always. So yesterday was in the 90s. Today, I think the high is going to be in the mid 70s. So we're happy about that.
Very, very good. Okay, thank you. Viewers, can I talk directly to you for just a second to give you some context for this? Michael Eddy from Purdue University, also in the Mid-Continent, was just awarded another National Science Foundation grant. Not an easy thing these days. And Mike's new grant, which I am part of, is focusing on Alaska tectonics. And my first thought went to Trevor. I met Trevor 2 years ago at a Penrose conference, 2 years ago this month, as a matter of fact, in McCall, Idaho. And I was very impressed with Trevor and his work thus far up in Alaska. So we're going to talk about a paper that Trevor sent me last night. And I have it printed out. I got my yellow pen, I got my printed paper, and I was sitting under the oak tree with our cat, and within 10 minutes, I'm like, holy cow, I got to get this kid on, man. This is exciting. So the topic today is the Denali Fault, and I'm just starting to get my head into Alaska again after a few years of not really thinking much about Alaska. So Trevor, is this work that you did for your PhD? Where were you studying? Who were you studying under? Let's start with that.
Yeah, so this particular paper was part of my PhD. It actually wasn't really the main focus of my PhD, if I'm being honest. It was just sort of something that came out of a lot of the what I call framework geology or kind of regional geology work that we were doing to address more topical questions related to mountain building along strike slip faults and things like that. So anyway, it's just kind of something that fell out of it. Um, uh, for my master's and my PhD, I was at UC Davis, University of California in Davis, and I worked with a woman named Sarah Ruskey, who has been doing geology in Alaska since I think 1980 is when she started her PhD. She did her grad work on Kodiak Island. And it was something you alluded to is that Alaskan geology is I think it's kind of overwhelming if you don't know where to look and what to read and the terminology and all this kind of stuff. To
Yes.
me, it's like Tibet is the same way. The Alps are the same way, where it's just like it's this impenetrable barrier of I don't know. I can read the stuff, but I don't know what anything means because of place names or like it's in a different language or whatever it is. And so I I completely understand where you're coming from with the Alaska thing. And so, the reason I'm talking about this is that Sarah is just one of these people that has been doing it, a long time. And so I got to, spend 8 years as a grad student working under her and learned a lot from her. And every time I talk, I still realize how naive I am about some things. But anyway, yeah. So Sarah Resky, and she was, trained up by one of the early Alaskan geologists and worked with the USGS through the 80s and stuff. And so she's just a wealth of knowledge and really feel fortunate to have her guide me into, learning something like Alaskan geology, which is, like I say, not the easiest thing to just pick up.
It's not easy, but I'm excited about this paper. So, viewers, if you go to my website, nickzentner.com, and click in the upper right, I think I'll have a placeholder. I'll say faults. How about? If you click on faults, the first paper and the only paper you'll find so far is a 2021 paper on the Denali Fault by Trevor and others. Um, what are a couple of headlines from that paper, and then we'll go deeper into it, Trevor. Why do you think I was excited? Oh, that's a stupid way to say it. What are a couple of the major messages from that paper?
Yeah, well, before I answer that question, I'll just also say that the paper was published open access. I try to do that whenever I can so that people, it costs a little bit extra money, but if I've got the money in a grant or something like that, I try to publish things open access so that anybody can read it.
Nice.
Um, so anyway, yeah, I'd say, the Spark Notes, the kind of headline messages, and actually with this paper, I made the main point is the title, which is something I've kind of grown to like doing. So, the main point is that the Denali Fault, which is a major strike slip fault that runs from British Columbia out to the Bering Sea has, at least in this one place where I worked, has 480 kilometers of displacement, and that displacement happened since about 52 million years ago. Um, Maybe a secondary highlight from the paper is that folks have argued, there's the Cordillera or Western North America is made out of these blocks of crust that have accreted to North America, collided. And folks have argued about whether, the thing colliding went under or whether North America went under the thing that collides. So we call that polarity.
Yeah.
And a sort of secondary outcome of this paper is I think we've got a pretty good grasp of the polarity in this one particular location where we can see that this thing that collided, which was basically an island arc complex, think like Japan or Sumatra, that would be a modern day analog, something like that, collided with North America about 80 million years ago. And that went under. North America was on top. So the thing colliding went under, North America on top. And so I would say um, that's those are probably the two takeaway messages. And actually, those rocks that record that collision got sliced in half by the Denali Fault. Some are left in Yukon Territory in Canada, and the others are in Alaska, where I did my PhD work. And that's how I got started on this whole thing is testing this correlation, which is not my idea. It's been around since the 70s, but we just have so much greater capability to do analytical work, and we have things like GIS and all this kind of sophisticated mapping software, sophisticated ways to date rocks nowadays that we didn't have 50 years ago. And
Right.
so I just kind of took new tricks to an old question, and generally my my outcome supports the stuff that they said in the 70s, which is just incredible for those folks that were out just mapping with paper and pencil. But anyway.
Okay, well, good. So there's all sorts of ways we can go here. Um, let's start with some basic, maybe rapid fire back and forth. It's a strike slip fault. Is it a right lateral dextral fault, the Denali fault?
Yes, yeah, right lateral dextral is the sort of fancy word we use for that, but basically rocks on the west side are moving to the north until they get into the curved part of Alaska, and then they start moving out to the west.
Okay. Um,
Um, yep.
and you are saying in this paper that all of that dextral motion started 52 million years ago or not?
So the 480 is since 52, but this is actually one reason I think this is an important paper, and I was really worked hard to get it out is that as you know, Nick, and maybe many of the viewers know, there's this controversy in Western North America about where things accreted and how far they moved to the north, right? We were talking about that a couple of years ago when we met. And one of the faults, well, so basically the paleomagnetic data say things have moved really far, and the geologic data say things have maybe not moved as far. Um, One of the faults that people call on to move things to the north is the Denali fault.
Okay.
And so, the important thing here is if we're going to call on major amounts of translation, we need to have precise knowledge of how much translation there's been and what time it took place. And so, an interesting thing about this paper is that a lot of this displacement is younger than what the paleomagnetic data would suggest.
Yes.
But there's also sniffs of deformation along the Denali Fault that there's an older fault that was a Cretaceous fault that could have been this major Baja BC fault or whatever. And the displacement we look at now, people are like, well, that's only, people used to say 400 kilometers. I would argue strongly it's 480 at the
Okay.
minimum. Um, but anyway, it's completely it's younger. It's all younger. And so, the net displacement, the cumulative displacement still counts for the paleomagnetic data because you're still moving things north, and we
Right.
drill the rocks for the paleomag where they are now, not where they were 50 million years ago, right? So it still matters, but what it means is that this displacement is both larger and younger than folks thought it was previously.
Okay, this is great. This is absolutely great. So my working idea for this coming winter, nothing official yet, but I'm thinking since I'm now on this Alaska grant, I want to spend this winter with the next A to Z series thinking about Alaska, possibly thinking about maybe making an inventory of all these faults, big and small, from Nicaragua to Nome, basically, and trying to just look for piercing points, trying to figure out what has been documented for sure on each fault. We just maybe start with that, and then we can kind of look back towards Baja, BC's type stuff. So, this paper we're talking about today, Trevor, you do have a piercing point, it seems. You have 2 points that used to be together. Can you describe those units that you're confident were once together and have now been offset by that distance that you were talking, 480 kilometers?
Yeah, yeah. So there's actually, I think if you look at the figure, maybe we can look here after we're done chatting.
Let's do it right
Um,
now. You want to
we
put a
want to do it
figure
right
on?
now?
Yeah.
Yeah, sure. Um, so I'll share my screen and we'll go to figures here. So we're seeing this
We got it.
map that's
Yep.
very colorful. All
Yes.
right. So all of these numbers here are geologic features, whether it's a fault or a pluton or a metamorphic belt or something like that. And
Mhm.
in this paper, I've got a table, and so they're numbered according to what number they show up in the table.
Can you
Um,
enlarge this a little bit? Sorry to interrupt
yeah,
you.
no problem.
Lower right. Yeah, thank you.
How about that?
Perfect.
So,
Thanks.
anyway, each one of these here, like number one, for example, correlates with number one here, and then so this is this dark green map unit, and then also correlates down here. So, I guess the point I'm trying to make right now is that if you look at the figure here, I've got 10 different things
Yeah.
that I'm using to track displacement. Um, the one that gives us a 480 kilometers is here is number five.
Hmm.
And number five in Alaska is a pluton, and in southwestern Yukon, so here's the Alaska-Yukon border right through here.
Thank you.
And this light pink color here is a pluton. Here they call it the Shakwack pluton. Here the pluton didn't have a name, but it's in a place drained by a creek called Ann Creek, so I named it the Ann Creek pluton.
Mhm.
Um, but anyway, they're the same age, same general composition. They're both cut by the fault. So this is the thing, is the people that map these, and I mapped it up here and somebody else mapped it down here.
Yeah.
We map these plutons going right up to the fault. So if you map something cut by the fault, you expect to find the other half of it somewhere along strike, right? And so basically that's my argument here with number five is there's these plutons. They intrude metamorphic rocks that are very similar. There's this light green unit here. And then they're also immediately north of these thrust faults here. So down here they call it the Shakwack fault. Over here we call it the Valdez Creek fault. So basically you've got a fault with a pluton above it and some schist in both places. And if you just measure that displacement, um, you get 480 kilometers of displacement. And so it's like we like to think of piercing points as truly one-dimensional features. It's kind of a piercing blob. These things are,
Yeah.
10, 15 kilometers in size. So
Right.
it's there is some uncertainty there, but that I think is the highest quality displacement uh, estimate from the work that I did.
Okay, Trevor, can you stop your share? This is a big moment right now. And it's why I got so excited. I think I even started yelling out loud to myself with my yellow pen last night in the backyard. Um, I doubt you're familiar with these units, but just north of Ellensburg is the Mount Stewart Pluton. And up
Hmm.
in southern British Columbia, there's the Spuzzum Pluton.
Yeah.
And that Pluton invades schist. And there's schist north of my town, and there's the settler schist across the border. And the Straight Creek Fault, you're nodding, so I guess maybe you are familiar with this. That relationship of these schists that are the same age and diagnostic features, and the two plutons, two different countries, by the way. We're not going Alaska and Yukon, we're going Washington to BC. And you just restore that frickin' Straight Creek Fault, and there are those two guys right together. And so you've got those units that are offset. Here's the same exact thing, Yukon and Alaska, the same idea with the schist and the plutons coming through. I just love that so much, and I'm just now curious and turned on probably too much at the moment. Maybe I'm getting too optimistic. How many more of those kinds of relationships exist where on these maps there's all these different names and nobody's really zoomed out mentally enough to try to put some of those stories together? Why did you do that with this situation? You said it wasn't the main thrust of your PhD. So did Sarah lead you this way, or did you kind of discover it on your own that there might be a connection?
Yeah, well, so oh man, so many things to talk about here.
I need to calm down. Come on, I
That's all
need to
right.
calm
So
down.
I'll just say, I consider myself generally literate in North Cascades geology. I'm sure you're familiar with this paper by Bob Miller that came out, I think, 2 years ago, where he tracks all those displacements on the Yalcum and Straight
Yeah,
Creek and all those faults, and
yeah,
familiar with Mike Eddy's work and all that stuff too. So yeah, I wouldn't consider myself an expert in North Cascades, but the similarities are striking. Um, and maybe we could talk about that another time, but
right.
I've actually given a presentation on this before too.
Okay.
Uh, but in any case, to answer your question, yeah, there are a bunch of other relationships like this. And actually another study that I supported, I was not part of necessarily, is that there's a bunch of younger plutons along the Denali Fault through the curved part in the Alaska Range. And my colleague Sean Regan has a cool paper from I think 2021 where he demonstrates, I think there are four plutons there that are all offset from each other by the Denali fault, and I can send you that paper, and I
Okay.
don't know, maybe want to have Sean on here at some point too.
Yeah.
Um, but in any case, why did I get going on this? Well, so the main topic of my thesis was, and maybe we'll go back to the screen share here.
Let's do it. Let's do it.
Um, the main topic of my thesis was to try to understand how strike-slip faults generate mountains. So, strike-slip faults, by definition, move rocks in the direction of strike, which is by definition a horizontal line.
Hmm.
So, strike-slip faults should move rocks horizontally, but in that case, why do we have, in many cases in the Cordillera, huge mountain ranges associated with our strike-slip faults?
Hmm.
And so if we look at this regional map here, this is Alaska, and then we got, there's no borders on here, but Yukon is generally here, and British Columbia is generally here. Here's Haida Gwaii for reference.
Thank you.
And this section that we're talking about is right here between that green blob and that green wedge there. Um, and along this section of the Denali Fault, like I say, there's 480 kilometers of displacement. And as you go out to the west, the displacement that's been documented out there is on the order of about 135 kilometers.
Hmm.
Um, and so what I was trying to understand is, why is there 300 kilometers of displacement difference between over here and over here?
Yes.
Um, and if you lose a bunch of that lateral displacement, can you generate topography by shortening or some other mechanism to
Hmm.
uplift those mountains? And so in order to address that question properly, we need to actually know how much displacement is on the Denali Fault. And so that was really what I was focused on, and I think the other papers that came out of my PhD tell that story. And I'll just say nowadays I've got a project down here in southwestern Alaska along the coast, and we're studying the Denali Fault down here, and I think that 134 kilometers of displacement is generally robust, but we've got other displacement markers down here, and I think it's kind of on the order of 150 to 200 kilometers of displacement along this western strand of the Denali Fault. And so there's definitely something funky going on where a lot of that slip, I'll just say goes away. It can't truly go away, but something happens, and it probably has to do with the curvature of the fault.
Very
So
good. In
anyway.
your little box, which again, I feel like there's a series of these talks coming on now. I don't want to take too much of your time, but I mean, I might be coming back and bugging you some more for
That's all
for
right.
this for this particular conversation in the paper. Which terranes are juxtaposed against each other now? Am I reading WCT as Rangelia or is that Alexander or both?
Yeah, so WCT is the Rangelia composite terrain. Some people call this the insular belt.
Okay.
Um, I I personally prefer the term composite terrain because it's more geologically meaningful.
Okay.
So this is Rangelia, Peninsular, and Alexander
Okay.
terrain. So then that's the light blue that goes from the Alaska Peninsula all the way through southeast Alaska into British Columbia.
And sticking with that, like you were drinking Kool-Aid from Basil a couple of years ago, like he had Rangelia in Idaho and then send the stuff north. Like, are we looking at a piece of Idaho uh, in that light blue someplace?
Yeah, I mean there it's man, what a can of worms. I mean something to think about is that Rangelia is or the Rangelia composite terrain, this amalgamated island chain is
Yeah.
really long. It covers a lot of latitude, and especially if you unbend all of this stuff, now you take the Alaska Peninsula and you bend it back around so that it's all straight.
Yeah.
This covers a huge amount of real estate and a huge amount of latitude. So, one of the cool things I think is that if you just do a simple restoration of the Tintina fault and the Denali fault based on the published slip estimates, all of these crustal blocks in here completely fill up the Columbia embayment. Um, and we've known that for a while. Sandra Wild's paper basically showed that, and Paul Umhofer had
Mhm.
a paper I think that showed that. And so you don't need the paleomag to fill the Columbia embayment necessarily.
Hmm.
The geologic slip estimates can do that. So by that logic, yeah, sure, this stuff hit Idaho. There's no problem with that in my eyes. And to be honest, I don't have a problem with the paleomag either. But
Right.
maybe a question is, what part of the insular terrains hit Idaho?
Exactly.
Was it the southern part? Was it the central part? Was it the, really far northern part? And I don't have an answer for that at this point in time, but
Yeah, let's save that. So the light blue on this tinier map that we're looking at, there's light blue going all the way down to Nanaimo, British Columbia, right?
yep.
That's a continuous Rangelia all the way down almost to the southern tip of Vancouver Island today.
Yes, that's correct. Yeah, most of the rocks on Vancouver Island are generally thought to be part of the Rangelia terrain.
Unbelievable.
And
Okay.
the Jurassic rocks there are generally interpreted as correlative with the peninsular terrain.
Okay. How about if we hop over the Denali Fault to the purple and the darker blue? That's Yukon. How do you pronounce that? Tanana?
Yeah,
Tanana?
Yukon Tanana
Tanana.
is the purple.
Yeah.
And then the darker blue is broadly Laurentian, so broadly North American.
Okay.
In this region, under where it says figure,
Yeah.
that's what we call the para-autochthon. And to be honest with you, I find the geology in that part of the world to be kind of confusing. I can't quite wrap my head around
Sure.
what has been written there. But yeah, basically we're looking at a fragment of North America that has had an arc built onto it, and part of this rifted away and then collided again is the interpretation.
Thank you. Trevor, can you stop your share again, please?
Yeah,
You're doing great. This is fun. This is fun. It's just like we're sitting outside the cabin in McCall two summers
yeah.
ago. I love this. I just love this, especially with a young guy who is continuing to work in Alaska. And I think that's the case. Oh, we're working on some coffee and everything's beautiful in Rapid City. Okay. Seems exciting to me. Are you fighting against an old guard who say take your 2021 paper and they're like, no way, no way. 480 kilometers since 52 million years ago. This guy's high. Is there some of that?
There's not in those words, but there's a little bit of that. Yeah. Um,
What is the traditional view of what we've talked about so far with these piercing points, these units, and this amount of offset younger than 52?
yeah, so I think the main challenger so there's another body of rock that's used to bracket displacement on the Denali Fault, and it's actually an incised stream channel. between what is region called the Nudezoten Mountains and the Desdiash Formation in Yukon. And basically, it's this incised marine canyon with these carbonate mega boulders in it. And they found it in both places. Um,
Wow.
and it's robust. I think it's the real deal. I think it's totally legit. And that displacement estimate gives 370 kilometers of displacement. Um,
How old is that thing?
well, that's the thing is that the rocks that are the walls of the channels are late Jurassic, and the mega boulders actually I think are Triassic, if I remember correctly.
God.
But the channel must be um, younger than late Jurassic because it's incised into the Jurassic rocks. So um, there's not actually, there's some assumptions here about the timing of that slip based on other rocks, not necessarily those rocks. Um, but anyway, so the way I dealt with this in the paper is that there's actually slip on multiple faults, and so this strand that has the 370 kilometers of displacement is only part of this story, and then there's another fault strand that basically is a shortcut fault that goes straight to the plate boundary, the Fairweather Fault, and that adds more slip to the Denali Fault as you go um, farther to the east, or
I
sorry, west.
I see.
And so that's what we call the Tachunda Fault, which had a big strike slip earthquake in 2002. So, basically what I'm doing is adding slip on these faults together, and I think there's a little bit of resistance to the way that I did that.
Okay,
Um,
fair
but
enough. Let's do two more things, and that's probably enough for today.
okay.
You mentioned the secondary kind of subheadline of this 2021 paper was evidence for subduction angle. Are we subducting eastward an oceanic plate, or are we subducting something? Are we shoving something underneath North America towards the east or towards the west? At least that's the nomenclature we've used in the past. Uh, which is it for your paper?
So in the rocks that I worked on in Alaska, and actually the rocks in Yukon as well tell this story, and other people have written about that. But they very clearly show that the structures that accommodate that collision dip toward North America. So the way that we interpret that is that the thing that collided, the Rangelia composite terrane, was stuffed under North America. So the structures dip in Canada, they dip to the northeast. In Alaska, because they've been rotated around, they dip to the north. Um, but either way, they dip under North America.
Under
So
North America.
North America was high, and then Rangelia went low. And the key thing here actually with that is the metamorphic grade of these rocks. We've got rocks that were at 25 kilometers depth, placed thrust on top of rocks that are basically dirt grade. So there is a very significant shear zone in both places that did a lot of that work of stuffing stuff under, and that thing it dips 45 degrees toward North America. So it's like hard to get around that.
Okay, well, this is sounding familiar to the California triad discussion, and we've got great evidence at such and such a time that I just can't see how we would have Western subduction. We've got blue schist and blah blah blah. It sounds oddly familiar up there. Maybe not oddly, I don't know. What time frame are we talking about for those rocks with this eastward subduction?
So the rocks were sedimentary rocks at 88 million,
Hmm.
and then they were metamorphosed by 82, and they stayed in the lower crust until about 55.
Wow.
So, and that shear zone that did all this work, it was active. Well, it probably has a protracted, multi-phase slip history, but that big metamorphic shear zone I was just talking about was active from about 65 to 56, something like that.
So this
And
big
so
Rangelia,
56, and then boom, 52, here comes the Denali Fault.
I see.
Yeah.
So down here at our latitude and further south, Basil took off talking about the hit and run and this big 100 million year old hit with Rangelia colliding with North America. What's your date up there with those rocks for the Wrangellia hit?
It's this is one of the tricky things is that it's different timing in different places.
Really?
And there's in my worldview, there's two reasons for this. One is that people talk about zippering or this diachronous closure, so it could have been earlier in the south and then got younger as you go north. I think that's logical. The
Okay.
other thing we need to think about is if you look at any island arc on Earth, there are promontories. They are bent. You look at Japan, you look at Sumatra, you even look at continental arcs, they're all bent. Look at the Cascades. It's bent. So even if you did an orthogonal collision, there'll be things sticking out that are going to hit before other things hit.
Hmm.
So sure, it might have hit at 100 in the south. I have no problems with that. In Southeast Alaska, it looks like it hit around 100 or 105. Where I worked, it looks like it hit around 85.
85.
Yeah, but here's the kicker. This is actually pretty cool. And I've been working on some restorations. So, we keep talking about how everything's bent, right?
Right.
Even if you undo the bending of Alaska, which is largely a late Cretaceous to Cenozoic feature, if you undo that, Wrangellia doesn't go totally straight. It's kind of like that kind of shape. So if you hit in the south here and then start shipping things to the north, you're actually going to converge in the north.
Yeah.
And you want to talk about the hit and run. The run was supposed to start at 85. Well, guess what? My hit in the north is at 85 and the thing
85.
bent. So you can hit in the south and then send it north. Once you do that, you're actually going to shorten
Hmm.
and hit in the north at 85.
Hmm.
So I I think we're just looking at, somebody's looking at the tail of the elephant, we're looking at the tusks. Out in Western Alaska, we're looking at the tip of the hair at the tip of the trunk of the elephant, you know? Um,
Yeah.
and I think it's important to take a, really regional approach with this kind of stuff. And, rather than saying, oh, it doesn't work because the timing's off, it doesn't work because the polarity's off or whatever, it's like try to make it all work, right? We have so much good data. And I think a lot of people are hesitant to accept the paleomagnetic data, but a lot of it is really good data.
Hmm.
Um, and we should try to use it. It's
Yes.
telling us something.
Okay, last thing. So, were you up in Alaska this summer, and where were you? Was it Denali fault related?
Yeah, yeah, I was in Alaska. I was I had mentioned on the map earlier, I've got a current project. Well, it's kind of actually winding down now. We're in the third year of our 3-year NSF project in a region way out in southwestern Alaska, Bristol Bay area. There's a little mountain range just onshore from Bristol Bay called on one side it's called the Wood River Mountains, on the other side it's called the Auckland Mountains. Um, and there's a state park there called Wood Tick Chick State Park. You should Google pictures of it. It's absolutely stunningly gorgeous. You can't drive there. You have to take a float plane or a boat
Hmm.
to get there. But anyway, so we've got a project looking at the uplift of those mountain ranges because the all most of Western Alaska is just kind of this broad plain that slopes off into the Bering Sea, but these mountains just rise right up from the coastline, and they're not that tall. They're something like 5 or 6 thousand feet tall, but they're really steep. And based on just some geologic arguments, the uplift must be sometime in the Cenozoic, so the last 65 million years. Um, but we're trying to figure out why, when those mountains were formed, and it's probably related to Denali Fault
Hmm.
slip. Um, and out there, we've got some displacement markers that um, give us something like 150 kilometers of slip since about 70 million years ago. So, yeah, so I was there a bit, and then when I came back to the road system, stopped off in a place called the Reindeer Hills, which is near a town called Cantwell. And there's some melange rocks. We could have a whole other conversation about what the heck melange is, but basically just really deformed, messed up rocks, which, as a structural geologist is like one of my favorite things. So, and that's just roadside stuff. So just doing some nerdy structure stuff on those rocks.
Nice. Well, Trevor, I appreciate your time today. This is all happening quickly. I emailed Trevor recently and said, "Can you send me a couple papers? I want to get started on this Alaska stuff." One thing led to another, and Trevor is coming to Ellensburg. I think it's official. I think we
Yeah.
agreed.
Yep.
Friday, October 10th.
That's right.
Is that right? Friday, October 10th of 2025. If you want to come to Ellensburg and listen to Trevor in person, he'll be giving a talk maybe related to this, who knows, but I think this is just the start of our Alaska correspondent living in Rapid City, South Dakota, but I feel like you're going to be a key person, at least for the next couple of weeks as I try to start thinking about this stuff. So thank you so much for your time today, Trevor.
Yeah, no problem. And I can, of course, send you more papers.
Okay, good, good. Well, please hold the line. Let me stop the recording, but we'll chat for a couple more minutes.
Sure,
Thank
yeah.
you for now. Over and out. Goodbye.
Bye, everyone.